So I think we'll go ahead and get started. So our first talk is going to be by Jacob Luhn, who is going to tell us about stars. So here is Jacob.
All right. So again, my name is Jacob Luhn. I'm a grad student here at Penn State University, and so I'm going to be talking about stars. How much can we learn from pinpricks of light? And as Michael said, the theme for tonight is sort of basics of astronomy, back to school. What I'm not going to be talking about is like what is a star, or how a star forms, or how a star evolves. And so the approach that I'm taking with this talk is more like the title suggests, how do we go from seeing these little pinpricks of light in the sky to saying something about these stars? So if you go someplace where it's very dark and you look out into the sky, I will just use the arrow keys then. My clicker is not working, and neither is this. Excellent. All right, so you go out to a dark place in the sky, you look up and you see thousands and thousands of these stars if you're someplace where it's dark enough. And all of these stars are these little tiny points of light. A star, I guess for background, since I haven't really explained it yet, a star, all you need to know is that it's a collapsing cloud of gas that gets hot and dense enough to fuse hydrogen. And this hydrogen fusion is what powers the star, gives off an incredible amount of energy, and makes a star bright. So all of these stars are in fact very big balls of hot gas, but they're just very, very far away. And so we can't see that it's a circle or a sphere. All we see is just a single point of light. And so the trick in astronomy then is to figure out how we can take these pinpoints of light and say something about it. And I think that's what makes astronomy a really cool subject. So here's just another image of the night sky, lots of stars. Now imagine you just grab one of these stars and say, I want to learn about this star. Just choose your favorite star in this image. And what are some of the questions that you might ask to learn about some of these stars? Like some fundamental questions. Anybody have a question that you would want to know about a single star in this image? Yes.
How big is it?
Yes, how big is it? Anybody else?
Chemistry. How hot is it?
How hot it is? Yes.
Chemistry.
Chemistry, yes. What's it made of? Yes. How far away? These are basically all of the ones that I have listed. Excellent. So I've written out a list of questions that one might ask. What is it made out of? How big is it? How old is it? How far away is it? How hot is it? How luminous is it? Or how much energy is it giving off? And so these are all really great fundamental questions that we want to ask. But unless you live in the Star Wars universe, you can't go to these stars and actually say, take a scoop out of the star and see what it's made out of. You can't put a ruler around the star and measure it. You can't stick a thermometer in the star and figure out what its temperature is. And so the next question that we have to ask is, what actually can we observe? And so what are some questions that we might ask about what we can observe of these stars? And this is maybe a little bit of a trickier question. Anybody have any guesses here as to what we can observe? Well, like I said, it's a little trickier, but here are some of the three main things that we can ask about these stars that we can observe. What color is it? You might notice that some of these are different colors. How bright is it? Some of these are obviously fainter than others. And how much does the star move? That one's maybe not quite as it comes to mind, but these stars are not quite static, and so that their movement is going to say something about the stars, and we'll learn about that in a bit. So in astronomy, what we're trying to do is tie these, what we call observables, into fundamental properties. And so I've listed here some of the questions that I asked, what the properties of the star that we're trying to understand. So mass, radius, temperature, age, composition, and distance. And so basically, most of our measurements in astronomy is one of these three things: either color, brightness, or position. Those are, or some combination of them. And so I need to introduce a few astronomy terms. The first is spectroscopy. So if you're measuring the color of a star, what you're doing is you're taking the star's light and you're breaking it into the various colors that make up that starlight. And so these are light at different wavelengths, colors. And so measuring that can tell us something about a star. You can measure photometry, the brightness. You're basically counting photons, particles of light that are entering your telescope, and you're saying, oh, if there's more photons, it's a brighter star. And so that's what we're doing with photometry. And then the last one here is when you measure the position of stars, you're measuring astrometry. So you're literally measuring stars, is what astrometry means. And so you're figuring out how these stars are positioned relative to each other. And so that's going to be the first one that I talk about, astrometry. So here we're measuring the positions of stars. So you might know that the night sky is not a static image. The stars are not static. They move about over the course of the night, and that's because the Earth is rotating. And so just like the sun rises and sets each day, the stars move across the sky. And so you can get some cool videos like this. It's maybe a little hard for people in the back to see, but you get these cool videos where the stars are moving across the sky over the course of the night. Or you can take a long exposure photograph. It's doing that. A long exposure where the stars have been, you can see their path across the night sky. As this red X indicates, this is not what astrometry is, though. This is a continuous, uniform movement among all of the stars. And what we're interested in when we measure astrometry is the positions of stars relative to one another. And so why do stars move? So the first main reason why a star might move is because stars are moving in space. They're not just sitting in the middle of space doing nothing. They're moving around the galaxy in some motion. And so this physical motion of stars that we see in the night sky, that portion is called the proper motion. And I won't talk much more about that. But the other primary motion of stars comes from the fact that the Earth is orbiting the sun. And so at different times of the year, you get slightly different perspectives of stars. And this introduces a parallax effect. And the best demonstration for the parallax effect is if you take your finger, put it in front of your face, close one eye. Everybody can do this along with me. Close one eye and focus on an object in the background. And then you move your head back and forth. And when you do this, it looks like your finger is moving relative to the background objects. If you put your finger further away, it moves not as much. And if you put your finger closer, it moves a lot. And so that's the parallax effect. And so the same thing happens with stars. So say in December, if we're looking at some nearby star, relative to some distant stars, we see one angle, and we get a view that looks like this. If we look in June, 6 months later, we're looking at the same star, but we have a slightly different angle relative to the background stars, and so we get a slightly different image. And as I said, if something's closer, it has a larger parallax, and if it's further away, it has less parallax. And so if we can measure the parallax motion of these stars, we can get an estimate of their distance. And so distance is a very important measure in astronomy, and it paves the way for a lot of the rest of the measurements that I'm going to be talking about. So how do we go from observables to fundamental properties? Well, we just learned if you can measure their parallax, their positions, you can get a distance. So the next thing I'm going to talk about then is photometry. And photometry, as I said earlier, you're basically counting photons. You're saying how many photons from this star are making their way into my telescope, and so how bright is it? That's a fairly straightforward thing. The trickier thing is the fact that a star's brightness in the sky depends on the actual brightness of the star and how far away it is. This makes sense. If you have two things that are the same brightness and you put one further away, it's going to look a lot fainter. And so in astronomy, we have to distinguish between the brightness in the sky and the actual brightness of the star. And so we call this the apparent magnitude and the absolute magnitude, how it appears, and the absolute. And magnitude is just some weird astronomer units for brightness. They're weird. So if we can measure the apparent brightness, how bright it is in the sky, and we know the distance from, say, a parallax, we can arrive at the absolute magnitude of stars. And this absolute brightness of a star, as I said earlier, relates back to how much energy it's giving off, because this is all coming from the fusion of hydrogen, and that's being radiated outward. And so we can go from an absolute magnitude to a luminosity, or something about the total energy output of the star. And this is going to come in handy because this is the only equation, I promise. The luminosity equals some constant, we don't care about it, times temperature to some power times radius to some power. So it depends on the temperature and the radius. So if we know the luminosity, we can sort of say something about the temperature and the radius, and we'll get to that in a bit. For now, these are sort of grayed out a bit because we don't really know. And we need to talk about spectroscopy next. So spectroscopy, we're measuring colors. So we're taking the starlight, passing it through some sort of prism or grating, something that spreads the light out into the various wavelengths of light that make it up, the various colors of the star. So when you do this for a star, you get something that looks like this. And you can think of this as saying, how bright is it at each of these colors? And so you can see that it's very bright in the greenish to bluish range for this star. And this band here in the middle that's marked by the word visible indicates the range of colors that are visible to the human eye. So this is where the human eye is sensitive in there. And you can see that stars emit light at colors beyond the range of human eye in both directions. And so this is called something called thermal radiation. And basically any mostly solid object that has a temperature gives off light according to this basic curve. The only difference is that things at different temperatures have a slightly different curve. So you can see here, here's a very hot star. It's 18,000 Kelvin, and it's emitting most of its light in the blue side of the spectrum. A cooler star at 6,000 Kelvin emits most of its light in the yellow region, and an even cooler star at 4,000 Kelvin emits mostly in the red. And so, as I said, all things that are mostly solid that have a temperature give off light according to this curve. Humans are 310 degrees Kelvin, and we're somewhere out in the infrared where human eyes can't see it. But if you are the predator, you can see Arnold Schwarzenegger's thermal radiation quite well. So we do give off thermal radiation, just our eyes are not sensitive to it. But the basic takeaway here is that the peak of these curves tell us about the temperature of the star. And if you remember, we have a luminosity, say, from our photometry. We measured how bright the star was. And now we have a temperature, and so now we can say definitively how big the star is. We can measure the radius. So that's where we stand. We still have a few more left to fill in, but I'm not quite done with spectroscopy yet. There's a little more we can get from spectroscopy. So I showed you those curves, the spectra of stars. Those were idealized curves. In reality, the real stellar spectra that we get look something a little more like this. You see that they're jaggedy. There are some dips where there seems to be missing light. And so this maybe makes it a little tougher to tell where the exact peak of this curve is if you want to find the temperature. But this is a classic case of it's not a bug, it's a feature. And we can use these, and they're actually called absorption features or absorption lines, to indicate the presence of elements in the star. And so what's happening is certain elements or atoms in the atmosphere of the star are absorbing some of that light, and so that's why it's missing. And they're absorbing at very specific and unique colors. So oxygen absorbs light at a very different color than, say, sodium or magnesium. And so you can use this to identify what the star is made of. So we've identified composition. We can identify elements in the star. We're still not quite done with spectroscopy. There's a little more, well, there's a lot more we can get, but for this talk, there's a little more we can get out of spectroscopy. So if you zoom in on a specific absorption feature, one of these dips of missing light where atoms in the atmosphere are absorbing light, this width of the feature depends on the density. And so if you have a higher density, you have more collisions between these atoms, and this affects the likelihood of absorption in the atmosphere. And so it turns out that if you have a higher density, you have a broader absorption feature. So from the width of the absorption features, we can determine the density of the star. And if we have a radius and we have a density, we can get a mass. And so we can use the absorption widths to arrive at the mass. So we're doing pretty good here. We've almost filled in all of these fundamental properties that I've listed. The last one here is age. And to talk about age, I have to introduce a plot that all astronomers in the room know, and that is the HR diagram. I can't give a talk about stars and not talk about the HR diagram. So this is the HR diagram. It's called the Hertzsprung-Russell diagram after the two astronomers who discovered it. And they noticed that if you plot the luminosity, how bright these stars are, their absolute brightness, as a function of their temperature, and this is where, as astronomers, we do things weird sometimes, and this temperature increases this way. So hot stars are to the left. They noticed that the majority of the stars fall along this diagonal line. And so we call this the main sequence. That's where most stars are found. It also turns out that if you look at the masses of these stars, the hotter, more luminous stars are the higher mass stars. And the cooler, less luminous stars are the low mass stars. And so there's a mass gradient here. And there's also these stars up here. These are sort of the leftover stars that aren't on the main sequence. So you might wonder, what's up with these? So they're very luminous, but they're very cool. And so what does that mean? Well, we have to bring up our luminosity equation again. So they have a really high luminosity, a really low temperature. So that means that they must be very big. They have a very large radius. And so these are our giant stars. These are the big, puffy stars that we see. And if you saw in the earlier slides a comparison between some of the sizes of stars, these are the real big ones. So what is this telling us? So the reason that we see most stars along this diagonal is a fact that these are the stars that are actively fusing hydrogen in their core. So it turns out that a star, when it's fusing hydrogen, it spends most of its life fusing hydrogen. So most of its life, it's going to be found along this main sequence. When it stops fusing hydrogen, it loses its energy source, and it needs to restructure a bit. And so what ends up happening is it expands and becomes a giant star. So it lives most of its life on the main sequence, and then eventually moves to the giant phase. So older stars are more this way. And so we can use models that sort of map out for a star of a certain size and mass how they move from the main sequence, this diagonal, towards the giant region. And so this is how we can estimate their age or how evolved these stars are. So we've filled in most of these things here that could have listed a whole bunch of other properties and gone on for a lot longer. I'm going to end here and just, I think that the fact that we can take these three observables, these fairly straightforward things, color, position, and brightness, and go to all of these things, mass, radius, temperature, age, about these stars that are just so far away we'll never actually be able to see. I think that's one of the coolest things about astronomy. And so just to summarize, how much can we learn from pinpricks of light? I hope I've convinced you that the answer is a lot. So I will take any questions.
So the giant stars are cooler, right? And they have a larger radius. So would it be fair? Could we like assume that there's a certain temperature that like things can't be hotter than, right? Because the stars are smaller, like hotter than some of the hottest stars.
Okay, let me see if I got your question. So it was, is there a temperature that stars can't be hotter than?
Right.
Essentially. I don't think I've ever thought about it that way. So Michael's answering for me. At some point, presumably the radiation pressure would blow things off. But the as you get to, so if we go back to the HR diagram, so you're talking about keeping going this way and what happens. So for the most part, these would be even more massive. These would be like the really, really high mass stars, not necessarily the giants. There are some that go around. Those are sort of the leftovers from high mass stars. In short, I don't know that there's a hard temperature limit, but perhaps.
Any other questions?
So are most of these observations done from the ground, or do you need to go to space to do some of these observations? Is there any advantage, disadvantage of going to space versus observing from the ground?
Excellent question. I don't need to repeat it because you said it into the microphone. Right. So, yes, you can do all of these observations from the ground, and they have been done from the ground. And we had, perhaps, I might say that astrometry might be one of the hardest to get precise from the ground. But it certainly is always better to go to space. You don't have to worry about atmosphere and things. And for instance, as we're continuing to go along and improve our technology and make things easier to go into space, we have the Gaia Space Telescope that just is changing how we do astronomy because it's getting super, super precise parallax measurements for millions, billions maybe, a lot of stars in the sky. Basically any star that you could look at and say, hey, what's the parallax for that? It's going to get it. And so we have super precise distances that are coming out like literally constantly. I mean, they're still going and still being refined. And so that just, as I said, it's sort of a building step, and distance is one of the first ones in that, and it paves the way for all the rest. So if you have a really, really precise distance, if you really know the distance to this star, it makes all of the rest of your measurements even more precise as well. So going to space is great, but also more expensive. Yes?
So we talked about taking the parallax measurement. You mentioned that you're comparing how it moves to the background stars. Don't you know how far the background stars are to be able to get an accurate estimate?
Yes. So if you don't, okay, sorry. The question was, when making the parallax measurements, don't you need to know how far away the distant stars are that you're comparing the movement to? Otherwise, you're going to get a not very precise parallax. And yes, you don't necessarily need to know how far away it is, but you do need to take into account the fact that those ones also have some slight parallax motion as well. And people write codes and think of that stuff and make sure that all of that is accounted for. And so it's more complicated than simply saying like, yep, it's moving back and forth. This is the thing. And that's what Gaia is doing. It's doing that and making a catalog, all of these stars moving subtly, and you can basically pull out the distance.
How are standard candles used?
Okay, so the question is, how are standard candles used for this? That's a good question. So in astronomy, we have things called standard candles, and these are objects that we know how bright they are ahead of time. They're very there's not much variation between stars. There's something very specific about these stars, and we know how bright they are, and that's just something that we know. And so we can then use the fact that we know how bright that they should be, and then compare it to how bright they look, and we can get a distance sort of without a parallax measurement. And so I think that's how it comes in here. You wouldn't necessarily need a parallax. Parallaxes are always good, especially if you have Gaia. Gaia is great.
All right, last question. What is your favorite star?
What is my favorite star? I don't think I have a favorite. The first one that popped into my... Yeah. I was actually just looking. I didn't realize that this isn't a real answer, but I was trying to figure out how many grains of sand there are on Tatooine. I learned that the two stars that Tatooine orbits are Tattoo 1 and Tattoo 2. So those are pretty cool. But I was going to say that the first one that popped into my head is Aldebaran, but I know nothing about it. It's a fun name. There's some cool names out there.